Alrighty, so let's make a Weir's diagram. Now, what I've got here is a template that I use to draw them. You should be able to find this on the website. Hopefully there will be a link shown in just a moment here. If you're trying to follow along, what I've also added is sketching in the word arterial here in black, atrial in blue, and ventricular in red, because those are the colors I'm going to use to trace the pressures. We're going to start, the core of the Weir's diagram is this area, which is tracing the pressures in those three areas. Also on the Weir's diagram, and stuff we'll add, is ECG up here, the state of the atrioventricular and semilunar valves, and the ventricular volume, the amount of blood in the ventricle. Now, usually the Weir's diagram is done for one side of the heart at a time. It looks pretty much the same on the two sides, but usually we draw this just to represent the left side of the heart. So in case you're wondering, those are the numbers that we're going to be using. Now, I do this differently if I'm trying to draw one to show people or if I'm trying to draw it to teach. So I'm going to start with drawing it to teach and then maybe show you how I would draw it to practice. Both of them are useful. So in order to teach, I'm going to do this using these markers. I'm going to use black, green, red, orange, and blue, just in case you're trying to follow along. And we're going to do it one phase of the cardiac cycle at a time, drawing in the vertical lines to indicate when we've reached a new phase. It's also going to be useful for me to have a ruler here to draw some straight edges, so I'll make sure I've got that. All right, let's start. So we began with the phase of the cardiac cycle, atrial and ventricular diastole. And during that phase, we said that the atrial pressure was a little higher than the ventricular because blood was coming to the atria and then draining into the ventricles. So we're going to have atrial pressure starting low and on a slightly upward trajectory. Ventricular pressure is going to be just below it and rising along with it as the blood in the atria is now draining into the ventricles. Pressure in the arteries is going to start significantly higher than those and be going slightly downward. The reason for that is this is representing the blood we pushed into the arteries on the last heartbeat. So it's still in there. The arteries are still under pressure. But as that blood is draining away to the rest of the body, that pressure is slightly declining. Now, we said that atrial and ventricular diastole lasts... Oh, actually, sorry, we should also add... We need to add in the status of the atrioventricular and semilunar valves. And I'm going to draw them in as shaded in when they're closed. So during this time, the semilunar valves, which I'm going to do in orange, are closed because the pressure in the arteries is higher than the pressure in the ventricles. So we'll shade that in, indicating the semilunar valves are closed during this time. The atrioventricular valves are open because the pressure in the atria is greater than the pressure in the ventricles. Now, that phase lasts until atrial systole. When the SA node fires off, we'll add the ECG later on, which makes the pressure in the atria rise as the atria contract. So we're going to draw that. It's a little bump in the atrial pressure. That, as it pushes extra blood into the ventricles, makes the ventricular pressure rise as well. And that has no particular effect on the arteries, so their pressure isn't really changed by that. It's still just falling slowly. So really, nothing has changed except the atria are pushing a little extra blood around. Alrighty. But then, the next thing that happens is toward the end of the atrial twitch, the ventricles contract. So this would be associated with the R wave on the ECG. And when that happens, the ventricular pressure should begin to rise. As it rises, one of the first things that happens is it's going to go above the pressure in the atria. So you'll notice that at this point, these two lines cross. I'm going to circle that because this is an important thing. So when the ventricular pressure rises above atrial pressure, that causes the atrioventricular valves to close. That's the beginning of isovolumic ventricular contraction. So at this point, we can add in a vertical line. Now we know it should line up exactly with this point. So let's just sketch that in. We'll do a sort of a dotted line here. I'm going to have that go all the way up and down my Wiggers diagram. Down here I'm going to note that this is where isovolumic ventricular contraction begins. I'm just putting an IVC down here. Now, at that point, ventricular pressure starts to rise quickly. That's also the point where the AV valves close. So I can start shading them in here. Ventricular pressure is now rising rapidly as the ventricles contract. Notice that arterial pressure is falling still, but as the pressure in the ventricles gets close, we're going to see a little bit of a bump as those semilunar valves start bulging outward into the arteries. The pressure in the atria is also going to rise a little bit. That's from that pushing those valve flaps backwards a little bit into the atria, compressing them a little bit. So this phase, isovolumic contraction, lasts until the pressure in the ventricles becomes higher than the pressure in the arteries. So again, here's a crossing. That's worth noting. And we're going to make a note of that one on here too. Let's see if we can line that up as well as we can. So this begins the next phase of the cardiac cycle, which if you look at your notes, you know should be ventricular ejection. I'm putting VE down there. Going back a little bit, my semilunar valves were still closed during this point, but as soon as the ventricular pressure goes above arterial pressure, semilunar valves are going to be open. Atrioventricular valves will still be closed. The pressure in the atria, which was pushed up a little by this, as soon as that blood starts leaving the ventricles, that pressure is going to fall low. And then as blood starts coming back to the atria, it's going to start rising again. The pressure in the ventricles will continue to rise, kind of reaching a peak and then starting to fall as the ventricles start to relax. Pressure in the arteries is going to rise along with it as all of that blood that we're pushing into the arteries adds to the pressure in those arteries. So this is what's going on during ventricular ejection in terms of pressure. My AV valves are closed during this whole time. That ventricular ejection period is going to last until the moment that the ventricles have relaxed enough that the pressure from the arterial walls is greater than the pressure in the ventricles. So we're going to represent that by, after just a moment here, the pressure in the arteries remaining higher, doing this, with a little bit of a bump here. This bump is actually the arterial walls springing back as the pressure in the ventricles drops down. When those two lines cross, that's another important moment. So we'll put in a divider here. See if I can get this to be close to vertical. That's the end of ventricular ejection and the beginning of isovolumic ventricular relaxation. So, pressure in my atria continued to rise during this whole time. AV valves were still closed. But notice, when the ventricular pressure drops below the arterial pressure, blood tries to flow backward from the arteries into the ventricles, But that's going to cause the semilunar valves to close, which means starting here, they're going to be closed again. The AV valves are also closed at this point because for them to open, the ventricular pressure has to drop below atrial pressure. So now that we're in this isovolumic period where both valves are closed, ventricular pressure continues to fall. Atrial pressure was continuing to rise, but at the point where the ventricular pressure drops below the pressure in the atria, right here, we have another crossing of pressure lines. Those are always important. So let's note that one. This is the end of isovolumic relaxation and the beginning of atrial and ventricular diastole. Now let's go back for a moment into isovolumic relaxation and look at what's going on in the arteries. Their pressure, once the ventricles stop pushing any more blood into them, starts to fall as the blood that was in those arteries starts draining away to the rest of the body. So that's now just going to be on a gradual decline. Now, my atrioventricular valves, which were closed all through here, will open as soon as the ventricular pressure drops low enough to let the atrial blood start coming in. So that's going to be where they open. My semilunar valves will remain closed. In terms of what happens in the ventricular and atrial pressure, ventricular pressure continues to drop. Once those atrioventricular valves open, the blood in the atria starts to drain into the ventricles, so their pressure starts to drop along with ventricular. But then, as we get toward the bottom, those pressures are both going to start to rise again, as the blood that is coming to the atria from the veins starts filling the ventricles as well. So that's going to be what it looks like here at the end. So that's the pressure part of the Wigger's diagram. We should go back and draw in one more phase change, which is where atrial systole began over here. So that's one other place where we change phases of the cardiac cycle. So this one is atrial systole, and we began with atrial and ventricular diastole. So there's part of our Wigger's diagram, the most important part, the pressure lines, which are probably the hardest part to understand. In a moment here, I'll add the ECG and the volume lines. All right, let's add the ECG first. So I'm going to move this down just a little to make it easier to see what we're doing. Now, the ECG is going to line up with specific events in this whole process. We know that, for one thing, atrial systole, the contraction of the atria, begins with the P wave. The P wave is when the signal is spreading across the atria. So we can just sketch that in right here. The P wave should line up with the beginning of atrial systole. Another event we can put in is that the contraction of the ventricles should line up with the R wave, this beginning of this contraction. Remember, the R wave is the spread of the action potential through the ventricles, which is the thing that starts their twitch. So our R wave should be lined up with this line, which is the beginning of isovolumic contraction. We can even put in a little Q, R, S complex there. The other wave on the ECG is the T wave, which is the end of the ventricular action potential. On the Wigger's diagram, that should line up roughly with the peak here. As the ventricular pressure starts to fall, that's coming with the end of the ventricular action potential. So the ECG should look something like this, with the R wave lined up with the beginning of isovolumic contraction, same as this valve closing, the P wave lined up with the beginning of atrial systole, and the T wave roughly aligned with the end of ventricular ejection, ending at about the time that this semilunar valves here close. Now that we've added the ECG, we can look at how much blood is in the ventricles, which is the last part of this Wiggers diagram. Now, for right now, just take my word for it that I'm going to start with the amount of blood in the ventricles fairly high, and it should be rising somewhat. This is because during atrial and ventricular diastole, blood is coming to the atria from the veins and then draining into the ventricles from the atria. So they've been getting blood for a while. And now that blood, they're still getting more blood as it's draining. Then we hit atrial systole, when the atria contract and push more blood into the ventricles. When that happens, the amount of blood in the ventricles rises and then up to a point, here. Now, during isovolumic contraction, this phase, IVC, we know that blood can't enter the ventricles because the AV valve's closed here. And we know blood can't leave the ventricles because the semilunar valves haven't opened yet. They won't open until here. So there's no way for blood to get in and no way for blood to get out, which means the amount of blood should be constant. This volume line should be flat during isovolumic contraction. Then, once the semilunar valves open, as they do here at the beginning of ejection, the amount of blood in the ventricles should start to drop as blood is now leaving the ventricles going into the arteries. So we're going to drop that off like this. And then, here, at the beginning of isovolumic relaxation, the semilunar valves close, so no more blood can leave the ventricles, but the atrioventricular valves haven't opened yet because ventricular pressure is still too high. So again, nowhere for blood to come in or out, so the amount of blood here should be constant, isovolumic. And then, once the atrioventricular valves open again, blood can start draining down into the ventricles from the atria, and the amount of blood starts to rise again. And then that's going to last until we come around to the next heartbeat and do the whole thing over again. So there you have a complete Wiggers diagram. Now, in a moment here, that's how I would draw it when I'm teaching, but in a moment here, I'll show you how I would draw it if I were practicing drawing it, which I strongly recommend you do. Okay, now I'm going to talk about how to draw a Wiggers diagram from scratch in a way that I think works better for practicing, rather than drawing it one little bit at a time. Instead, if you draw it this way, you'll have an easier time making everything come out in a way that helps you to understand it. You're still going to use ventricular pressure in red, atrial pressure in blue, and arterial pressure in black. We're still going to color the semilunar valves as closed. We'll shade it in orange when they're closed, and the AV valves in green when they're closed. So that's our plan. Now, if you're drawing this from scratch, what I recommend starting with is the ventricular pressure line. You're going to draw that all the way across. So when you're drawing the ventricular pressure line, it should start on the low side, slowly rising. It should have a little bump, and then it should have a large rise, arc, fall, and then be rising again. So you should try to look for a shape that looks something like this. It should drop to lower than where it started, and then try to have it rise about to the same level as where it started by the end of the graph, because this is supposed to represent one cycle. Now, once you've done that, you can already identify a few things. This is going to be atrial systole. That's where the atrial blood is going to be coming into the ventricles. And this is mostly going to be ventricular ejection. The next thing I would add is actually not the atrial, but rather the arterial pressure. That should start fairly high up. I would aim for about 2/3 of the way up the graph, and it should start on a decline, slowly dropping. Right before it crosses the ventricular pressure, bump it up a little, have it cross, and then follow just under the ventricular pressure, and then part way down, but not as low as you came in, bump up again, and then be on a downward trend. Again, trying to end it roughly where you started it. Now, Remember, this is happening because the blood that we put into the arteries is draining away to the body, which means the pressure is falling, although still high because the arteries are under a fair amount of pressure. It bumps up just a little as the ventricular pressure rises toward it, and then it follows along with the ventricular pressure, but just under it, just a little below ventricular pressure. That's because when the ventricles are squeezing, that pressure that they're applying is going into the arteries. So the arterial pressure is also rising, but it's a little lower. Then this represents when the pressure in the ventricles falls below the pressure that the walls of the arteries can exert. Now that you have these two places where these lines have crossed, you can add in vertical lines there to indicate a phase in the cardiac cycle. Try to line it up so it's straight up and down, more or less. Doing this on graph paper might be helpful. So there's one of them. There's another one. We know that this represents ventricular ejection. This is the time when we've opened the semilunar valves and then closed them again. So I can even label that ventricular ejection. And I know that this is the time when the semilunar valves are open, so I could even shade in that they are closed until that point and closed again afterwards. So I've already got part of my Wigger's diagram done. Now, the next thing I would put in is the atrial pressure. And that one's a little bit trickier. You want to start it just above the ventricular pressure, rising along with it, going up during atrial systole, and then right after atrial systole, it should cross, go up a little until this line, then drop off, go down below where it started, start to rise. And you want to aim to have it cross ventricular pressure a little bit out here. When it crosses, it should drop along with ventricular pressure and then rise along with it. The idea here is that the atria are filling with blood from the veins, which is why their pressure is going up. That blood is draining into the ventricles. Here's where the SA node is going to fire, so the atria contract and we get a little bump. Then the R wave is going to fire about here, which means that's when the ventricles contract. This rise is from the ventricular pressure pushing the walls back upward into the atria, though not opening the valves. This lines up with when the semilunar valves open. When the blood starts leaving the ventricles, that relieves some of that pressure, atrial pressure drops off, but then as venous blood starts flowing back into them, they rise until the AV valves open, when ventricular pressure drops low enough, and then the blood that was building up in them drops into the ventricles, their pressure goes down, but venous blood continues to flow in, so it starts rising again. And now we can add a couple more phase changes. Here, where the atrioventricular valves close, that's a change in the cardiac cycle, so we can line that one up. And here, where the AV valves open again. So that one's a little bit harder to line up vertically, because I don't have a lot of references, but close enough. So we now know that this one, the time between when the AV valves close and the semilunars open, that's isovolumic contraction. This one, between the time when the semilunars close and the AV valves open, is isovolumic relaxation. And we know that after that is atrial and ventricular diastole. We also know that my AV valves close here, stay closed until that ventricular pressure drops low enough, so that's when they open again. Alrighty, now, we can now indicate one last phase. That should be here at the beginning of atrial systole. There's no obvious clear point to do it, just put it about where that atrial pressure starts to rise. So something like, I don't know, maybe about here. Sounds fine. So that's atrial systole. Now we can add the last two parts of this. We want to add the ECG. We want to make sure that the P wave lines up with the beginning of atrial systole. The R wave lines up with the beginning of isovolumic contraction. And our T wave is roughly aligned with the end. That's kind of a little bit early maybe, but it's close enough, of ventricular ejection. And we can fill in our ventricular volume as well. Volume should start high and rising. During atrial systole, it should get bumped up. Flat during isovolumic contraction. Dropping off during ejection. Flat during relaxation. And then rising again during atrial and ventricular diastole. So that's how I would draw this if you're practicing. It's a little faster that way, and it gives you practice at making sure you know why these lines are crossing, that those are the differences in the phases of the cardiac cycle. I recommend trying this, try it, then check it, figure out what you did wrong, go back and try it again. Once you feel like you can draw it, make sure you can label what's happening at each of these crossings. So, for example, this one is the atrioventricular valve closing. This is the semilunar valve opening, semilunar valve closing, and the atrioventricular valve opening. I would practice that several times until you can do the whole thing like that. I won't ask you to do it. I don't know how I would do that on an online test. But once you can draw this well and clearly label and line everything up the right way, that's when you know that you really understand how the heart works. Good luck with that.